Hi, so today we're going to discuss the wave properties of particles, quantization of angular momentum in the Bohr model, the quantum particle, the double slit experiment, the uncertainty principle, the wave function and probability density, a particle in a box, the Schrodinger equation, and tunneling through a potential energy barrier. So in the previous video of quantum mechanics, we discussed Bohr's model of the hydrogen atom. And this model has many limitations. So for example, it does not explain the spectra of more complex atoms, nor the variations of spectral line intensities, or also the splittings observed in certain spectral lines, okay? Also, it does not enable us to understand the interaction between atoms. So between 1925 and 1926, the theory of quantum mechanics that addresses the limitations of Bohr's model was developed by Schrodinger and Heisenberg and others. And as we have seen in the previous video, quantum models of the photoelectric effect and Compton effect agreed with the experimental results and showed that light behaves as particles known as photons, each with energy of hf and momentum of hf over c. But we also have seen in the previous videos of light that light and other electromagnetic waves exhibit interference and diffraction effects which are explainable only with the wave model, okay? So the question is light a wave or a particle? And it turns out that it depends on which phenomena is being observed. So it was concluded that light has a dual nature and it exhibits both wave and particle characteristics, okay? So the particle model and the wave model complement each other. And one of the possible explanations out there, and this is still a very active field of research, is that a subatomic entity is more fundamental than either a wave or a particle, and that this entity has the potential to take on either form of wave or a particle. Depending on what the observer do, or in other words, that the mind can influence which form it takes, which means that the observer and the object are not independent, okay? So the macroscopic world that we experience every day is just a surface layer of reality, and the quantum world is a more fundamental layer. And as we shall see in the following, quantum mechanics is fundamentally unpredictable as opposed to the deterministic laws of classical physics, okay? So in general, quantum mechanics gives a more fluid and flexible nature of the world, and a complete understanding of the nature of light, for example, requires the particle and the wave model as complementary to each other. Okay, so neither model can be used to describe all properties of light. So we will now discuss the wave properties of particles. So it also turns out that not only light has a dual nature, but matter also has a dual nature. And in 1923, Louis de Broglie postulated that perhaps matter also have wave as well as particle properties, okay? And in the previous section, the previous video of quantum mechanics, we have seen how the momentum of a photon is given by E over c, which is equal to hf over c equal to h over lambda. So it shows that the photon wavelength can be found from its momentum, okay? So de Broglie suggested that a material particle of a momentum p can also have wave properties and a corresponding wavelength. So for a non-relativistic particle, the momentum is given by mv, where v is the particle speed. So de Broglie wavelength is given by lambda equal to h over p equal to h over mv. Also, using the analogy with photons, de Broglie postulated that particles obey the relation E equal hf, given by Einstein. And so the frequency of the particle is equal to E over h. So next we will show how the wave nature of particles was experimentally verified. So we will now talk about the Davison-Germer experiment. So the Broglie proposal showed that if particles such as, for example, electrons have wave-like properties, they should exhibit diffraction effects, right? So in 1927, Davison and Germer succeeded in demonstrating this and measuring the wavelength of electrons. So the discovery was made by accident because originally the experiment they were making was of the scattering of low energy electrons projected at a nickel target in vacuum. Then an accidental break in the vacuum system caused the nickel surface to be oxidized, and then it was heated in a stream of hydrogen to remove the oxide coating. And then when electrons were scattered from the target, there were intensity maxima and minima at certain angles. And it was because the nickel formed crystal regions due to heating, and the regular crystalline structure served as a diffraction grating for the electrons, okay? And so the result confirmed the wave nature of the electrons and the Broglie relation P equal to h over lambda. And later, diffraction patterns formed by hydrogen atoms, helium atoms, and neutrons were observed, which further confirmed the wave nature of particles. So one of the practical applications of the wave nature of electrons is the electron microscope. And the figure here shows a transmission electron microscope, and it has a much higher resolving power than an optical microscope due to the very short wavelength of the electrons, right? Because as we mentioned in the videos of light, the wavelength of the waves used to illuminate an object puts a limit on how much details can be resolved. And because the electrons can be accelerated to very high kinetic energies, they have very short wavelengths. And so an electron microscope can resolve details about 100 times smaller than those distinguished by an optical microscope, okay? And the electron beam in the microscope is controlled by electrostatic or magnetic deflection, which can focus the beam and form an image, and the image is formed on a monitor, okay? So this here shows the image of an ant using a scanning electron microscope. So let's take this example here. So suppose we have an electron which has a mass of 9.11 times 10 to the minus 31 kilogram, moving at a speed of 1 times 10 to the power 7 meter per second. And we want to find the Broglie wavelength of this electron. And also suppose we have a macroscopic object of mass of 0.05 kilogram moving at a speed of 60 meter per second, and we also want to find the corresponding de Broglie wavelength, okay? So for the electron, the wavelength is equal to 7.27 times 10 to the minus 11 meters, and this wavelength can be detected by diffraction techniques. For the macroscopic object, it is equal to 2.2 times 10 to the minus 34 meter. And as you can see, this wavelength is much smaller than any aperture the object could pass through, okay? And this is why it is not possible to observe diffraction effects and the wave properties of macroscopic objects. So we will now discuss the quantization of angular momentum in the Bohr model. So one of the insights of de Broglie is that interference effects can be applied to electron waves bent into a circle around the nucleus, as you can see here. So the same way a plucked guitar string supports only standing waves that have nodes at its ends, like here, this can be applied to the electron wave, and all possible states of an electron represent standing wave states, where the electron waves are bent into a circle, as you can see here, and each state has its own wavelength, speed, and energy. So this here shows orbits containing 1, 2, and 3 wavelengths, okay? So as we said, this situation is analogous to that of standing waves on a string, that has certain resonant frequencies of vibrations, right? So we can imagine these 2 points here being joined together and the vibrating string being bent into a circle, okay? So the quantization of the angular momentum of the electron proposed in Bohr's theory can be shown to follow by using the Bohr hypothesis of the standing waves of the electron around the nucleus. So the allowed Bohr orbits are the ones where the electron matter waves form standing waves, okay? And so they are the orbits when an integral number of wavelengths exactly fits into the circumference of the circular orbit. So the orbit, the allowed orbit, is when n lambda is equal to 2 pi r, where n is equal 1, 2, 3, etc. And r here is the radius of the orbit, okay? So because the Bohr wavelength is given by lambda equal h over mv, and since h bar is equal to h over 2 pi, we may write this equation here in this form. So we substitute for the Bohr wavelength, and we get an expression for the angular momentum. So as you can see, this is precisely Bohr's condition for the quantization of angular momentum. So the standing waves of the electrons that fit the orbits have discrete frequencies that correspond to the allowed wavelengths. So if n lambda is not equal to 2 pi r, a standing wave pattern cannot form a closed circular orbit because the waves will interfere destructively, okay? So in this section, we will show how a wave packet like this one here is a reasonable way to model a particle. So far we have considered the particle model and the wave model. So in the particle model, an ideal particle has 0 size, right? Also in the wave model, an ideal wave has a single frequency and is infinitely long, like this one here. So a particle differs from a wave in that it is localized in space. So now suppose we have a wave of a certain frequency, like this one here, with one of its crests at x equals 0, and if we draw another wave of the same amplitude but of a different frequency, like this one, also with one of its crests at x equals 0, then the result of the superposition of these two waves will form a beat, like this one here. So as you can see, when we have a single wave like this one here, it has the same amplitude everywhere in space. So no point is different from any other point in space. So let's imagine that we add more and more waves to these two waves here, each with a different frequency, and let's assume that each new wave is added with one of its crests at x equals 0. Then at x equals 0, all of the waves will add constructively, okay? And if we include a large number of waves, we get a wave packet like this one here. So this wave packet is localized in space because it is different from other regions, because the result of the superposition of the waves in other regions is 0, right? And this small region of constructive interference is known as a wave packet. So the wave packet can represent a particle because it has the localized nature of a particle, okay? And we will now also show how the group speed of a wave packet is identical to the speed of the particle. So to show this, let's consider two waves with equal amplitudes and different frequencies, f1 and f2. And we have omega is equal to 2 pi f and k is equal to 2 pi over lambda, okay? So using the superposition principle, we have y equal y1 plus y2, and we get this equation, and we can use cosine a plus cosine b is equal to 2 cosine a minus b over 2 cosine a plus b over 2, and we get this expression here. So as you can see, the second factor here represents a wave with a wave number and frequency that is equal to the average of the values of the individual waves. And the first factor here represents the envelope of the resulting superposition wave, right? So this is the envelope here. So as you can see, this envelope has the form of a wave, right? And it can travel with a different speed than the individual waves. So for the individual wave, the speed is given by v phase equal to omega over k. It's known as the phase speed. Because it represents the rate of advance of a crest on a single wave, okay? So it represents the advancement of a point that has a fixed phase. So the phase speed of a wave is equal to the ratio of the coefficient of the time variable t, which is omega, to the coefficient of the position variable x, which is k, okay? As you can see here from this equation. So also we have the first factor here in this equation has the form of a wave, and so its speed is given by Vg, the group speed, okay? And it's equal to the coefficient of time over the coefficient of x. And as you can see here, the coefficient of time is delta omega over 2, and the coefficient of x is delta k over 2, okay? So it's equal to delta omega over delta k. And it is known as the group speed, okay? And it represents the speed of the wave packet, okay? It is the speed of the wave packet. So for the superposition of a very large number of waves that form a wave packet, then the group speed is given by d omega over dk, okay? And if we multiply by h bar, we get this expression. And h bar omega is equal to h over 2 pi f equal to hf equal to e. And h bar k is equal to h over 2 pi over lambda and is equal to p. So we can write the group speed equal to dE over dP. So let's consider now a free particle moving with a speed v that is small compared to the speed of light. Then the energy of the particle is its kinetic energy given by half mv square equal to p square over 2m. And if we differentiate it with respect to p, where p is equal to mv, and we get the group speed is equal to d over dp of p square over 2m, and is equal to the speed of the particle v, okay? And so the group speed of the wave packet is identical to the speed of the particle, okay? So in this section, we will consider a hypothetical experiment in which electrons are fired at a double slit, as you can see here. So a parallel beam of monoenergetic electrons is incident on a double slit. The widths of the slits are small compared to the electron wavelength, so that we don't include diffraction maxima and minima, as discussed in light video 3. We have an electron detector screen placed here far from the slits at a distance L much greater than D, where D is the separation between the slits. So if the detector collects electrons for a long period of time, a wave interference pattern for the probability of arrival of electrons, which is the number of counts per minute, forms on the screen. And it is found that the angle theta at which a maximum of the intensity of the electrons is formed is described by the same equation as that of light. So it is d sine theta is equal to m lambda, where m is the order number and lambda is the electron wavelength, okay? So this experiment clearly demonstrates the dual nature of the electrons. So the electrons are detected as particles here, at a specific spot on the screen at some instant of time, but the probability of the arrival at that spot depends on the intensity of the two interfering waves, okay? So now suppose we lower the beam intensity so that one electron arrives at a time at the double slit. So in the classical view, the electron would go through either slit and one would not expect an interference effect, right? Because there isn't a second electron that goes through the other slit and interfere with the first electron. But an interference pattern is still observed if enough time passes for many electrons to arrive at the detector screen here, okay? One at a time. So the figure here shows a computer simulated interference pattern for a beam of electrons incident on a double slit. And as you can see, the interference pattern becomes clearer as the number of electrons reaching the screen increases. So here it shows the screen after 28 electrons has arrived. Then at 1000 electrons, a pattern of fringes begins to form. Then when 10,000 electrons arrive, the pattern of the computer simulation is similar to the actual pattern found in the real experimental demonstration of the double slit electron interference pattern. And so these results show that the electron passes through both slits simultaneously, okay? And if one tries to find experimentally which slit the electron goes through, the act of measuring will destroy the interference pattern. So we will now discuss Heisenberg uncertainty principle. So suppose we measure the position or velocity of an object at a certain instant. Classical physics shows that although experimental uncertainties or error factors can exist, there is no fundamental limit to how precise the measurement can be. Or in other words, a better apparatus and experimental procedure can give a better and more refined measurement, and there is no fundamental limit to that, okay? But quantum theory showed that it is fundamentally impossible to have infinite accuracy when making a simultaneous measurement of a particle's position and momentum, and this is known as Heisenberg uncertainty principle. And it states that if the measurement of the position of a particle is made with an uncertainty of delta x and the simultaneous measurement of its momentum is made with an uncertainty of delta px, then the product of the two uncertainties can never be smaller than h bar over 2. So the uncertainty principle also means that we cannot know the future because we cannot know the present, right? So as we said in the previous slide, in the quantum particle model, a moving particle is regarded as a wave group like this one here, okay? And the particle that corresponds to this wave group may be located anywhere within the group at a given time. But the probability density is maximum in the middle, okay? And we will see this more in the next section. So suppose the wave group is narrow, like in this case here. So the narrower the wave group, the more precise the particle position can be specified, right? But the wavelength of the waves in a narrow wave group is not well defined, right? Because there are not enough waves to measure lambda accurately. And because the momentum is equal to h over lambda, it means that for a narrow wave packet, the particle's momentum mv is not a precise quantity. And so the more we know about the position of the particle, the less we know about its wavelength, and therefore the less we know about its momentum. So now suppose we have a wide wave group like this one here, and as you can see, such a wave packet has a well-defined wavelength, right? And so the momentum that corresponds to this wavelength is a more precise quantity. But the width of the wave packet is now too great to be able to say exactly where the particle position is at a given time, right? And so the more we know about the particle's momentum, the less we know about its position, and vice versa. And so it is impossible to know both the exact position and the exact momentum of an object at the same time. And also another form of the uncertainty principle concerns energy and time. So for example, if we want to measure the energy E emitted during the time interval delta t in an atomic process, we have this equation. And it can be found using a similar argument to the one we used for position and momentum, where we can consider the horizontal axis in the wave packet here to be time rather than the spatial position x, okay? And so the corresponding variables would be frequency and time. So if we have less time, it will restrict the accuracy with which we can determine the frequency of the waves. And so the more exact the measurement of time, the greater the uncertainty in the measurement of frequency and vice versa. And since the frequency is related to the energy of the particle, by E equal hf, we get here this equation, okay? So let's solve now two examples. So in the first example, a hydrogen atom has a radius of 5.3 times 10 to the minus 11 meters. And we want to estimate the minimum energy an electron can have in this atom using the uncertainty principle, okay? So using this equation, and if we substitute for delta x, we get delta px is greater than or equal to 9.9 times 10 to the minus 25 kilogram meter per second. And this value of the momentum shows that the kinetic energy can be found from this classical expression instead of the relativistic expression, and we get the kinetic energy is greater than or equal to 5.4 times 10 to the minus 19 joules, which is equal to 3.4 electron volt, okay? And note that the kinetic energy of an electron in the lowest level of a hydrogen atom, as we have seen in the previous slides, is equal to 13.6 electron volt, okay? So for the second example, suppose an excited atom gives up its excess energy by emitting a photon, and if the average period of time that elapses between the excitation of the atom and when it radiates is 10 to the minus 8 seconds, then we want to find the inherent uncertainty in the frequency of the photon. So the uncertainty in the emitted photon energy is given by this equation, and if we substitute for delta t, it's greater than or equal to 5.3 times 10 to the minus 27 joules. And the corresponding uncertainty in the frequency of the light, because E is equal to h mu, is greater than or equal to 8 times 10 to the power 6 hertz. And this represents the limit to the accuracy with which we can determine the frequency of the radiation emitted by the atom. So we will now discuss the wave function and the probability density. So first, we will go back to photons and see the connection between the probability per unit volume of finding a photon and the intensity of the radiation. And this gives another connection between particles and waves. So suppose we have an electromagnetic radiation. The probability per unit volume of finding a photon in a certain region of space at a certain instant of time is proportional to the number of photons per unit volume at that time, right? Which is n over v. So probability per unit volume is proportional to n over v. And n over v is proportional to the intensity of the radiation, right? And so from this you can see the link between the particle model and the wave model. And as we have seen before, the intensity of electromagnetic radiation is proportional to the square of the electric field amplitude, okay? So I is proportional to E square. And so the probability per unit volume of finding a photon is proportional to the square of the amplitude of the electromagnetic radiation associated with that photon, okay? And a parallel relation exists for material particles. So the probability per unit volume of finding a particle is proportional to the square of the amplitude of the wave representing that particle. And so as we have seen in the previous section, the wave associated with every particle is the de Broglie wave, okay? And so the square of the amplitude of that wave is proportional to the probability per unit volume of finding the particle. And so the amplitude of the wave associated with the particle, the de Broglie wave, is known as the probability amplitude or the wave function and has the symbol psi. And in general, for a system of particles, the wave function psi depends on the positions of all the particles in the system and also on time. So this is the complete wave function for system of particle, and Rj is the position of the jth particle in the system. Also, for many systems, including those that we will include in this video, the wave function psi is a separable function in space and time and can be written as the product of the space function for one particle of the system and the time function e to the power minus I omega t, okay? And omega is the angular frequency of the wave function. And this is the form of the wave function when the potential energy of the system is time independent, okay, and depends only on the positions of the particles within the system. And in such case, all important information is written within the space part of the wave function here, and the time part is just e to the power minus I omega t. So this psi Rj is often complex valued, okay, and this quantity here, psi absolute square, which is equal to the complex conjugate of psi times psi, is always, this quantity here is always a real and a positive quantity, and it is proportional to the probability per unit volume of finding a particle at a given point at a certain instant of time. So this wave function contains all of the information about the particle, okay? And this probability interpretation of the wave function was first suggested by Max Born in 1928. Then later, Erwin Schrodinger proposed the wave equation that describes how this wave function changes in space and time. So suppose we have an ideal free particle with a momentum that is precisely known, px, and its wave function is a sinusoidal wave, and its wavelength is given by the Bohr equation here, okay? And because it's a free particle, it has an equal probability of being at any point along the x-axis, right? So the wave function is given by e to the power I kx, and k is equal to 2 pi over lambda is the angular wave number, and a is a constant amplitude, okay? And the full wave function is given by this equation. So a e to the power I kx times e to the power minus I omega t equal to this, and we can write it in terms of cosine plus I sine, okay? So as you can see, the real part of this wave function has the same form as the waves that are added together to form a wave packet, as we have seen in the previous section, right? So although we cannot measure psi here, this quantity, psi absolute square, is measurable. And it is known as the probability density, and it represents the relative probability per unit volume that the particle will be found at any given point in the volume, okay? Or we can also say that for a volume element dv surrounding some point, so the probability of finding the particle in that volume element is absolute psi square dv. So let's now consider a one-dimensional system where the particle must be located along the x-axis. In this case, the probability of finding the particle in the infinitesimal interval dx is equal to px dx, equal to absolute psi square dx, okay? And because the particle must be somewhere along the x-axis, the sum of the probabilities over all values of x must be equal to 1, right? So the integration from minus infinity to absolute psi square dx is equal to 1. And note here that any wave function satisfying this equation is known as a normalized wave function, okay? And the meaning of this normalization is that the particle exists at some point all the time, right? The particle is there somewhere. So as we have seen from Heisenberg principle, that it is not possible to specify the position of a particle with complete accuracy, it is still possible to find absolute size square which specify the probability of observing the particle in a small region surrounding a given point. And this probability is given by a PAB integration from A to B absolute size square dx. So this probability is the area under the curve of the plot of psi square versus x, right? Between the points x equal a and x equal b. So as you can see here in this figure, the area under the probability density curve from A to B represents the probability of finding the particle in this interval, okay? And also experimentally, this probability of finding the particle in an interval near a certain point at a certain instant of time is finite, so it has a value between 0 and 1. And we will see in the following section that the wave function psi satisfies a wave equation known as Schrodinger equation, okay? So one can find psi from this wave equation, but as we said, psi is not measurable, but all measurable quantities of the particle, such as its energy and momentum, can be derived from knowing psi. So let's consider, for example, if we know psi and we can calculate the average position at which we find the particle after many measurements, okay? And this average position is known as the expectation value of x and is defined by this equation. So it's the integration from minus infinity to infinity of the complex conjugate of psi times x times psi dx, okay? So the bracket here is to denote the expectation value. And in general, the expectation value of any function fx associated with the particle can be found from this equation, okay? So let's consider the example of a particle in a box. So we have a particle that is confined to a one-dimensional region of space, and this problem is known as the particle in a box problem, okay? So according to classical physics, if a particle is confined along the x-axis between two impenetrable walls, there is no restrictions on the values of the particle's momentum or energy, right? It can bounce back and forth, and its motion is easy to describe. But according to quantum mechanics, this is not the case. And we need to find the wave function that is consistent with this situation. So first, the walls are impenetrable, and the probability of finding the particle outside the box is 0. And so the wave function psi x is 0 for x less than 0 and x greater than L, where L is the distance between the two walls. Also note here that the wave function must be continuous in space, otherwise its derivative at the point where it is not continuous would be infinite, right? And this will lead to problems when solving Schrodinger equation, which we will discuss in the next section. So for these two impenetrable walls, an appropriate boundary condition for the wave function, if it is 0 outside the walls, is that it must be 0 at the walls, okay? And so psi at 0 is equal to 0 and psi at L is equal to 0. And this shows that not any wave function is allowed, but only those that satisfy this condition, okay? So the figure here shows the potential energy of the particle environment system as a function of the particle's position, x, okay? When the particle is inside the box, the potential energy of the system does not depend on the particle's position, and we can consider it to be 0. Also, to ensure that the wave function is 0 outside the box, we let the potential energy of the system to be infinite if the particle is outside the box. So an appropriate wave function is equal to a sine 2 pi x over lambda, and we will show later why this is an appropriate wave function by solving Schrodinger equation for a particle in a box, okay? So we apply the boundary conditions for this function, and we get psi at L is equal to 0. So this gives 2 pi L over lambda is equal to m pi, and this gives lambda equal to 2L over n, okay, where n is equal to 1, 2, 3, etc. And so as you can see, only certain wavelengths for the particle are allowed. And each allowed wavelength corresponds to a certain quantum state of the system, okay? So n is the quantum number here. So psi nx is equal to a sine 2 pi x over lambda, and if we substitute for lambda, we get a sine n pi x over L. And the figures here show a plot of psi nx and psi nx absolute square as a function of x, okay, for the first 3 allowed states of n equal 1, 2, and 3 for a particle in a box. And as you can see, psi n can be positive or negative, okay, but absolute psi n square is always positive. And this is consistent with absolute value of psi n square representing the probability density, right? Because if it's negative, it would be meaningless. We cannot have a negative probability. And also, as you can see, psi n absolute square is 0 at the boundaries, and it is also 0 at other points. For example, for n equal 2, it's 0 at x equal L over 2. And for n equal 3, it's 0 at x equal L over 3 and 2L over 3, okay? And the number of points, as you can see, of absolute value of psi n square being 0 increases by 1 each time the quantum number increases by 1, okay? So going back to the wavelength of the particle, so because it is restricted by this condition, it follows that the momentum of the particle is also restricted to certain values, right? So the particle cannot have any momentum as classical physics suggests, but only certain allowed values given by nh over 2L, okay? And so the allowed values of the energy here, En, which represents the kinetic energy of the particle, because as we said, the potential energy is 0 inside the box, is given by this equation. So En is equal to h square over 8m L square n square. And the figure here shows the energy level diagram for a particle confined to a one-dimensional box of length L, right? And as you can see, the energy of the particle is quantized. So the particle cannot have any energy as classical physics predicts, but only certain energies are allowed. Similar to how the energy in the hydrogen atom is quantized that we discussed in the first video of quantum mechanics, right? And the lowest allowed energy is E1 equal to h square over 8m L square, corresponding to n equal 1. And it is known as the 0-point energy, okay? And the next excited states can be written as n square E1. So the second allowed state has an energy of 4E1, and then the next allowed state is 9E1, then 16E1, and so on, okay? So notice here how the state for which n is equal to 0 and e is equal to 0 is not allowed, okay? So according to quantum mechanics, the particle can never be at rest. And this is not what classical physics predicts, because according to classical physics, the state of E is equal to 0 is an acceptable state, right? So the particle least allowed energy is equal to E1, corresponding to n equal 1, and as we said, it's known as the 0-point energy. So let's consider an example of an electron and an alpha particle, each confined to its own box, and suppose these two boxes are identical of the same length L, okay? And we want to find the ground state energy for each particle. So as you can see from this equation, the lighter particle, which is the electron, has a higher ground state energy than the alpha particle, because the smaller the mass, the higher the ground state energy, right? And according to this equation, both particles will have the same wavelength in the ground state, because the two boxes are identical. So let's consider another example here of finding the ground state energy and the speed in that state of an electron confined to a box of length of 0.5 nanometers, and for a macroscopic object such as a ball of mass of 0.5 kilograms confined to a box of length of 50 meters. So for the electron, the ground state energy is equal to 2.4 times 10 to the minus 19 joules, which is equal to 1.51 electron volts. And the speed of the electron in that state is given by this equation and is equal to 7.2 times 10 to the power 5 meters per second. So for the macroscopic object, E1 is equal to 4.4 times 10 to the minus 71 joules, and the speed is 1.3 times 10 to the minus 35 meter per second. And as you can see, this speed is too small, right? So we can consider the object to be at rest. And this is why the state of E is equal to 0 is an acceptable state in classical physics for an object in a box. And as we said before, as this macroscopic object moves around, it will move through many quantum states that are so close together in energy that we cannot observe the transitions from one state to the other. Instead, we experience it as a smooth transition and variation in the speed and energy of the object, right? So the quantum nature of reality is not evident at the macroscopic scale. So in this section, we will see how the waves associated with particles satisfy a wave equation in a similar way of how an electromagnetic radiation satisfies the wave equation, as we have seen in the electromagnetic video 6. So this wave equation was developed by Schrodinger in 1926, and when solving problems in quantum mechanics, one can find the solution of this equation and then apply the appropriate boundary conditions to the solution. And this will yield to the allowed wave functions and energy levels of the system, okay? And then all measurable quantities for the system can be calculated from the wave function. So for a particle of mass m moving along the x-axis, and if the potential energy of the particle and its environment is ux, then Schrodinger equation is given by this equation. And this is known as the time-independent Schrodinger equation. And here we will not discuss the time-dependent Schrodinger equation, okay? We will consider it in other videos. So the system here is the particle and its environment. And the first term here in the equation represents the kinetic energy of the particle multiplied by the wave function. And so this equation shows that the total energy is a constant and is equal to the kinetic energy plus the potential energy. So if one knows the potential energy ux for the system, one can find the wave functions and the corresponding energies of the allowed states of the system, right? So note here that sometimes the potential energy U may vary discontinuously with position, and in that case the equation can be solved separately in different regions, okay? But the obtained wave functions in the different regions must join smoothly together at the boundaries between the regions. For psi x to be continuous, okay? Another condition is that psi x must obey the normalization condition, and for this to happen, it must approach 0 as x approaches plus or minus infinity, okay? And also it must be single valued, and also d psi over dx must be continuous, because if it's not continuous, we would not be able to evaluate d square psi over dx square at the point of discontinuity. So the easiness of how to solve Schrodinger equation depends on the form of the potential energy Ux. So it turned out that Schrodinger equation was extremely successful in explaining the behavior of atomic and nuclear systems, whereas classical physics failed to explain those systems. Also, when quantum mechanics is applied to macroscopic objects, the results agree with classical physics. And this, as we said in the previous video of quantum mechanics, is known as the correspondence principle. So we will now analyze the particle in a box problem with Schrodinger equation. So as we have seen, the potential energy is represented by this diagram here. And so sometimes this problem is referred to as a particle in a square well problem, okay? So in this region from 0 to L, U is equal to 0, okay? And if we substitute in Schrodinger equation, we get this equation. And K is equal to square root of 2me over h bar. So the most general solution of this equation is given by psi x is equal to a sine kx plus b cosine k. So a and b are constants determined by the boundary conditions, which are psi at 0 is equal to 0, and this gives b is equal to 0, and psi at L is equal to 0, and this gives KL equal to m pi, where n is an integer. So if we substitute for k, we get this equation, okay? And from this, we get the energy levels En, okay? And if we substitute for k here, we get this equation. And from the normalization of psi and x, we get the value of a equal to square root of 2 over L, okay? So this is the wave functions, the allowed wave functions for the particle in a box. So let's find the expectation value of the position x of the particle in the state of the quantum number n. So this is the expectation value, and if we substitute for psi conjugate and psi, we get this equation, okay? And if we integrate this, we get here this expression, and so the expectation value of x is equal to L over 2. And this shows that the expectation value of the position of the particle is at the center of the box, right, at L over 2 for all values of n, even though, for example, for the state n equal 2, the probability has 0 value at the midpoint, as you can see, of the box, right? But the expectation value of x we calculated here represents the average position, okay? So we will now discuss tunneling through a potential energy barrier. So suppose we have this potential shown here, okay? The potential energy of the system is 0 everywhere except in the region, this region of width L, okay, where the potential energy has a constant value U. So this type of potential is known as a square barrier, and the value of U is the barrier height, okay? So the barrier has a finite height and width. So suppose a particle of energy of E less than U is incident on the barrier from the left. So according to classical physics, the particle should be reflected by the barrier, okay? Because if the particle can exist in region 2, its kinetic energy would be negative, which is not allowed classically, right? Because as we said, the energy of the particle is less than the barrier height. So the particle does not have enough energy to cross the barrier, okay? So classically, regions 2 and 3 are both forbidden for a particle incident from the left, okay? But according to quantum mechanics, the particle can access all regions regardless of its energy. But the probability of being in a region that is classically forbidden is very low, okay? But still, there is a probability for the particle to be there, and the probability is not zero. Also, from the point of view of the uncertainty principle, the particle can exist within the barrier as long as the time interval during which it is there is short, okay, and consistent with the uncertainty relation between time and energy. So if the barrier is relatively narrow, the short time interval can allow the particle to move across the barrier. So using Schrodinger equation, there is a solution of the equation for each of the three regions. So in region 1 and 3, the solutions are sinusoidal, as you can see. And in region 2, the solution is exponential. And we will not go through the details of finding the solutions here. And by applying the boundary conditions that the wave functions in the three regions must join smoothly at the boundaries, the full solution can be found, and the plot is shown here, okay? And because the probability of finding the particle is proportional to psi absolute square, the probability of finding the particle across the barrier in region 3 is not zero, okay? Which is contradictory to classical physics. So this crossing of the particle through a barrier is known as tunneling or barrier penetration. The probability of the tunneling is described by the transmission coefficient T and the reflection coefficient R, okay? The transmission coefficient represents the probability that the particle penetrates to the other side of the barrier, okay? And the reflection coefficient here represents the probability of the particle being reflected by the barrier, okay? And because the incident particle is either reflected or transmitted, we have T plus R is equal to 1. So for the case when T is much less than 1, which is when the barrier is very high or very wide, which means when U is much greater than E, an approximate expression for T is given by this equation, where C is equal to square root of 2m U minus E over h bar. So in contrast to the deterministic classical mechanics, in which the trajectory of an object can be calculated to a high precision from the knowledge of the initial position and velocity of the object, quantum mechanics, as we have seen here, shows that the fundamental laws of nature are probabilistic, okay? So tunneling is a result of the wave nature of matter, okay? And many phenomena can be explained by tunneling, and it also has many applications. So one of these phenomena is the alpha decay, and it involves the emission of alpha particles, which are the nuclei of helium atoms, by unstable heavy nuclei, okay? So for the alpha particle to escape from the nucleus, it penetrates through a barrier that has a height that is several times greater than the energy of the nucleus alpha particle system. So occasionally, an alpha particle tunnels through the barrier and escapes the nucleus. So another phenomena that involves tunneling is nuclear fusion, which is the basic mechanism that powers the sun, okay? So within the core of the sun, protons must come close to each other and fuse together to form a deuterium nucleus. But according to classical physics, since the protons electrically repel each other, they should not be able to overcome and penetrate the barrier caused by their repulsion. But according to quantum mechanics, the protons are able to tunnel through the barrier and fuse together. So one application of tunneling is the scanning tunneling microscope, or the STM, okay? And it uses tunneling to create images of surfaces with a resolution at the scale of the size of a single atom. And it consists of a small probe with a very fine tip that scans very close to the surface of the specimen. And the tunneling current is generated between the probe and the specimen, okay? And it is related to the probability of the tunneling of the electrons through the vacuum separating the probe and the specimen. And so this tunneling current is sensitive to the barrier height, which is proportional to the distance between the tip and the specimen. And the tunneling current is maintained at a constant value by raising and lowering the probe as the surface is scanned, okay? And this is used to generate an image of the surface of the specimen. So the figure here shows an image of a gold surface with it shows atomic rows, and the size of this image is 10 by 10 nanometers, okay? So in the following I included 2 solved examples. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.